right, so hopefully that helps build your intuition about how eigenvectors and eigenvalues work. Now let's look at the actual equations. We are going to say that x is an eigenvector of a matrix, we'll just call it M, with eigenvalue lambda if, get this, the following equation is true. Mx equals lambda x. Okay? Now, when I first learned this, I remember saying, whoa. That's an equal sign? Because this is majorly screwed up. This doesn't even make any sense, I thought. Because on the left-hand side, you have these humongous things going on, right? Let's say M is a 7 by 7 matrix. You've got 17, 55, 38, 19, blah, 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 blah. A zillion numbers over here, 39 or 49 of them, times this long thing. And then you're trying to tell me that's equal to that times x? I mean, that's just a plain old number, like 3 times this thing. So it's not even obvious at first glance that dimensionally this makes any sense. But it does when you realize that this is what matrix vector multiplication does, right? If you take a 7 by 7 and you multiply it by a 7 by 1, you are going to get a 7 by 1 answer. And if you take an ordinary scalar and multiply it by a 7 by 1, you're going to get a 7 by 1. So it does make sense dimensionally, and actually it's kind of interesting, right? We're saying that taking this whole matrix and letting it operate deeply, computationally on this entire vector actually gives the same result as just scaling the vector. And that, of course, is what we mean by an eigenvector. When you transform it using this matrix, you get back a simply scaled version of it. And if lambda is higher, then it's going to end up growing the vector for its output, and if lambda is less than 1, it's going to end up shrinking it. If lambda is negative, which can be the case, by the way, it's going to make the vector point in the other direction, right? So that's the definition of an eigenvector and eigenvalues, is that simple equation, okay? And what we're going to say here is that all, I'm going to put an asterisk here, n by n matrices have n distinct eigenvectors. Which you remember I said before, after we had found our 2 eigenvectors for that one M matrix, right, we found that I believe it was -1, 1/2, and all of its friends, all the things in its direction was an eigenvector, and we also found that 4, 4, and everything in that direction was an eigenvector. This had an eigenvector, or eigenvalue of 2, this had an eigenvalue of 1/2. You remember that point? I said there's no point in looking for any more because it's a 2 by 2 matrix was M, and therefore it's only going to have n distinct eigenvectors. So here what I'm saying is all n by n matrices have n distinct eigenvectors, and distinct, just to be clear, that means different eigenvectors, right? So this here is a different eigenvector than that one is, okay? Now I put an asterisk here, so let me come down and do the asterisk. I lied. Almost all matrices have that. Occasionally you will get a weird one. So here's a weird one, and I just happened to create this. You actually kind of have to concoct it by trial and error to get a weird one. Here's a matrix, I'm going to call it W for weird. This doesn't look weird, but actually if you work this out, you're going to discover that it has an eigenvector of 1, 1 with an eigenvalue of -1. And its other eigenvector is also 1, 1, also with an eigenvalue of -1. Okay, so this plays the same role with matrices as like a duplicate root does in ordinary algebra. Like if I just made some thing here, if I said f of x equals 3x squared minus 100x plus 5. This is going to end up having 2 roots, meaning 2 places where it crosses the x-axis. But occasionally you'll get one that only has 1 root because it's a double root. Like if I just said, 14x squared, we know that that only touches the x-axis in one place, which is right there. That's because this is a double root, right? The same root appears twice. So that's essentially what's going on here. And as I said, almost all the time you luck out and don't have that, and you have n distinct eigenvectors, which are all different from each other. By the way, the official name for weird is the word, it's a long one, undiagonalizable. That's what we call weird matrices. And you're not going to understand why it's called undiagonalizable until the next segment, when I talk about diagonalizing a matrix, which you can do with every matrix that's not weird in this sense. And that's what the spectral theorem is going to turn out to be based on, okay? So, bottom line is this. If I give you just a random Joe matrix that's 10 by 10, it's going to have 10 eigenvectors to it. Yes, it's true that there are some really, really weird cases where it has fewer than 10. It'll never have more than 10. But for most of the time, you're never going to get one of those by accident. It's kind of like a singular matrix, right? If you just pick a random matrix, fill it up with random values, you're not going to get a singular one. All the stars would have to be aligned against you in order for that to be the fact, okay? So generally speaking, there's n eigenvectors to an n by n square matrix. Each one of them is different. Each one of them has its own eigenvalue, and whichever one is the highest eigenvalue, as we know, is the dominant eigenvector.